Part 4. The nature of polyprotic acids. Not all acids, like this acetic acid, dissociate by forming only a single H plus ion. Some can release several H plus ions, like this phosphoric acid that releases a whole 3 H plus ions, and these can have multiple dissociations. Acids that can release more than one H plus for each acid molecule are known as polyprotic acids. So, for example, in this case, H3PO4 can release 3 H pluses. When it is dissolved in water, the H3PO4 can give 3 H pluses to the 3 water molecules that are required for each H3PO4 molecule, and this yields 3 hydroniums, because 1, 2, 3, 3 hydroniums, and the PO4 3 minus anion. However, this reaction is deceptively simple. This does not actually happen when H3PO4 dissolves in water and then dissociates. What actually happens is that this reaction, this total reaction, happens in many steps, and this is important, and I'll explain why. Usually, when this phosphoric acid dissociates in water, it does so in multiple steps. It does so in this case in 3 steps. So in the first step, the H3PO4 gives an H to the H2O, forms an H3O plus, and gets left with this H2PO4 minus, which lost an H to the H2O, which made H3O plus. Then this H2PO4 minus can lose another H to the H2O to form another H3O plus, and this H2PO4 minus now becomes HPO4 2 minus. And then this HPO4 2 minus can lose another H to the H2O, and this forms another H3O plus, and this HPO4 2 minus transforms into PO4 3 minus, with all of the hydrogens completely removed. Now, why does this acid not just release all of its H ions in one go, like in this reaction? Well, this is because right here, after H3PO4 lost one of its H's to H2O to form an H3O plus and H2PO4 minus, you can see that the H2PO4 minus has a negative charge. H3PO4 is neutral, but H2PO4 has a minus charge. Since these H's, these H ions, are positive, it becomes more difficult for this H2PO4 minus acid to lose additional H's because it is negative and the H plus is positive. So to take off another H, like in this reaction, it becomes more difficult because this negative charge pulls back these positive H pluses that get pulled off. So each time you tear off a H from the H3PO4, it becomes more and more difficult to remove an H plus, because this thing becomes more and more negative from -1. So first it becomes -1, then -2, and it becomes more and more difficult to take an H away from the H3PO4, and then the H2PO4 minus, and then the HPO4 2 minus, because these get more negative and pull the H pluses back stronger. And that's why H comes off one at a time. Now, because it becomes more and more difficult to take an H plus away from these more and more negative acids, the Ka's for each of these reactions is different. In fact, for the first reaction, the Ka is the highest because it's the easiest to take off an H from H3PO4. Then the Ka for the second reaction is lower because this is more negative and it's more difficult to take away positive H pluses. So this Ka is lower. And then the Ka here is the lowest because this is the most negative portion right here. and therefore it is even more difficult to take off an H+, and therefore this acid here dissociates very poorly, because it does not really tend to yield H+, because it's so negative it tends to pull them back. So the Ka3 here is very low. So these Kas for each progressive reaction are labeled Ka1, Ka2, Ka3. The Ka1 is much higher than Ka2, and the Ka2 is much higher than Ka3. Essentially, the progression goes like this, where the Ka1 is higher than Ka2, and the Ka2 is higher than Ka3. And these are very large differences on many orders of magnitude, usually for these types of polyprotic acids. So now that you know how the strength of these reactions differ, you can see how, let's say the H3PO4 on its own is a weak acid. So most of this acid remains undissociated. We can also see that basically the H3PO4 concentration is going to be pretty high here. It's going to be one of the highest concentrations of substances in the solution. Furthermore, since the Ka1 for this H3PO4 is the highest out of these Kas, the H2PO4- concentration is also going to be fairly high than, let's say, HPO4 2- concentration, the PO4 3- concentration, since more of it gets produced because of a higher Ka. It is then, of course, used up, some of it's used up in the second reaction, but very little because the Ka2 is significantly smaller than the Ka1. Also, another ion that is pretty common here, relatively common than, let's say, the HPO4 2- and PO4 3- is the H3O+. Because again, each of these reactions contributes H3O+ to the solution. So you can say the most common ions in this reaction are the H2PO4- and the H3O+ ions. And a common substance would then be water, obviously, because this entire thing is happening in a large amount of water, and the H3PO4 that we added, since it's a fairly weak acid. Now, this is what happens when this polyprotic acid dissolved in water. The H's come off one at a time, and there is very little, let's say, of this PO4 3- and very little of this HPO4 2- because the Ka's are very small. However, if this polyprotic acid, H3PO4, is combined with a base, a very strong base, a strong base, like NaOH is sodium hydroxide. It's a very strong base, and it tends to really grab these H's away from the H3PO4. Then we essentially ignore these K1, K2, K3. Because let's say we add enough NaOH to take away 1 H from this H3PO4, it is gonna take that 1 H away no matter what. No matter what this Ka1 is, this NaOH, let's say 1 NaOH added to 1 H3PO4 molecule, is definitely gonna take that H away. So you see the H plus gives off, the OH- of the NaOH takes this H plus and forms H2O. Now let's say we add H3PO4 to 3 NaOH. 3 of these for every single molecule of H3PO4. In this case, since there are 3 of these OH-, it's going to take all 3 of these PO4, no matter if the K2 is lower than K1 or K3 is lower than K2, no matter if it's harder to rip off, it gets progressively harder to rip off these H's. This NaOH, because it's such a strong base, it's going to take all of these 3 H pluses at one time, and it's going to produce 3 water molecules, because 3 OH- and 3 H plus form 3 water molecules. So basically, to keep in mind, I just want to say, in the future you might have to use this, is that when dissolving in water, yes, the Ka1s do matter. But when dissolving this phosphoric acid in a strong base, the relative differences between these Kas don't really matter. All you have to know is that if there is only enough NaOH to get one of these H pluses from this H3PO4, then it will take this one H plus, because these H pluses do come off one at a time. But if there's enough NaOH to take all three of these H pluses, it's going to take all three of these H pluses. One at a time, yes, progressively, because again, these Ks do become weaker. And this acid does give off H pluses one at a time. But because there's such a strong base, it's going to rip them off. Like, there is no question about that. All of them. It's not like water where a lot of the stuff remains undissociated. The base is so strong that it rips off these H pluses fairly easily. So if there's enough base to rip off one, it's going to rip off one. If there's enough base to rip off three, it's going to rip off three. It's not like water where a lot of these H3PO4 remains undissociated and the H pluses are kept by this H3PO4. The base completely takes them away.